policy pi, right? So let's say you are in a maze and you can go up, down, left, or right. You have 4 actions. Now, according to the optimal policy, you would just go in one particular direction that helps you get out of the maze, right? So that is the optimal action for that particular state that you're in. So what would the probability of that action be for the optimal action? Would it be 0.5? Would it be 1? Like, what does it mean for an action to be optimal? That you want to keep taking that action and not take any suboptimal actions, right? So that is what optimality means by definition. And yeah, so like someone said in the chat, probability of that action is 1, right? So if we are not just evaluating any policy pi, but we are evaluating the optimal policy pi star, what would this be? This would just be for that action 1, right? So if I were to write that out, would it look like this? That I'm taking this part and writing it here, and then whichever action maximizes this is the optimal action, right? I could sum over all possible actions and their probabilities, but I know that the probability of the optimal action is 1, right? And then the probability of all other actions is 0. And so this will just end up being this term for the action, which is the optimal action. And so whatever action maximizes this expression is the optimal action. Does that make sense? So we just took the Bellman equation and thought about what it would look like for the optimal policy if instead of pi as, it was pi star as, right? And so it is just this expression. And this is called the Bellman optimality equation, because this is the Bellman equation for the optimal policy. Okay, so let's get back to what I was just alluding to in the previous slide about dynamic program, right? So, okay, so does this series look familiar to you? Series of numbers. Okay, so can anyone tell me what numbers are? Okay, so Pia says Fibonacci, right? So, and that's correct. So let me give this some indices. The first number is 0, second number is 1, and so on. Now, is there a connection between these numbers? Like, are they related to each other in a certain way, right? The answer is yes, that f of 2, okay, let me say f of 3 is f of 1 plus f of 2, right? So f of 3 is f of 2 plus f of 1. Similarly, I can write f of 4, f of 2 plus f of 3, correct? 2 is 1 plus 1, right? And so how this looks like a structure like this, right? That f3 depends on f1 and f2, f4 depends on f3 and f2, f5 depends on f3 and f4. Now, if I were to compute f5, I could compute all of these numbers all over again. But if I have their results already stored, I could just use their values, right? So f5, I can directly compute as f3 plus f4 instead of breaking f3 back into f1 and f2, going back to the base case of the recursion, which are these two numbers, right? So we are storing the solution of some subproblems that we know the solution to, and then using them for computing the values of the previous states, right? So that's what the sort of structure we had, that if we have a problem like this, like we had in the previous slide, we can compute the value of this guy, and then we can, to compute the value of this state, we can just bootstrap off the value that we already computed here, right? Along with the reward that we see along the way. And then to compute the value of this state, again, some reward here, and then we can just add this value instead of adding all of these rewards all over again, because we have done some of the effort in storing those values here, right? So yeah, so this is just some clever bookkeeping that helps us be more efficient. Okay, if you're talking, there's a comment that if you're talking about the Fibonacci series, then tending to infinity, that has the geometric series with the common ratio as equal to 1. Yeah, that's a good observation, that the golden ratio is a number that is found a lot in nature, and as many people have studied extensively in mathematics, physics, and all of our natural laws, right? But yeah, that's a discussion for later. I could give a whole talk on that too. It's a very, very interesting. Okay, moving on. So I guess I promise this is the last slide with a bunch of math. And from now on, from this point on, we'll just use these intuitions and then talk about some algorithms, right? Let me get back to that question. Okay, so we wrote that the value of a state is the expected return starting from that state when following policy pi, right? And then we expanded it as this Bellman equation. But this is the value of a state, right? Now, what if we wanted the value of a state after we take a certain action, right? So this is called an action value, because, state value, action value. Now, this is the expected return starting from state S and taking action A and then following policy pi thereafter, right? So it is similar to this, just that we don't just start from state S, we also take an additional action and then we compute the expectation, right? So these are very closely related quantities. Can someone guess what the relation between these two quantities is, right? So this is starting from a state, and then you take action A, right? So do you need to sum over all the probabilities of the actions, or you've already taken one of these actions, right? And so that gives you just the remaining expression, which is this. You've already taken some action, so you don't need to sum over those probabilities again. And what remains is just this. Okay. Now, if you look at these two things again, can I rewrite this expression or maybe simplify it a bit based on what I know here? I can, right? I can just write V pi of S, sum over all actions, Q pi of SA, right? The action values for starting from that state for all the actions that we are summing over. And we just replaced it with this expression, right? Okay, cool. Now, can we plug this expression back in here? We wrote this for state S, but you can also write it for state S prime, right? What do we get? Again, all of this is initial stuff plus V pi of S prime now expanded using this equation. Okay. Hope everyone's with me so far. Okay. Now, we have an expression for action values purely in terms of action values, right? No more state values. Now recall that we wrote the Bellman optimality equation for state values like this. Now, can you guess what the optimality equation would be for action values? Recall what we did. We took the policy and then replaced it by the best possible action in that state, right? And so the best possible action would lead to the maximum value of this quantity. So the maximum value of this quantity. So that's why we got a max of A instead of the sum or all pi. So with that intuition, can you do the same for this guy? Since we are looking at the optimal policy, would there be a sum or all possible actions, or would there be one optimal action? As pointed out in the chat, is the optimal policy following the greedy approach? Yes, that's exactly right. That's a good observation. So this is the this is what the greedy policy would get. And so if we were to do the same thing for action values, you would get this, right? Again, just the pi is replaced by the max over the actions in the next state. Okay, so I'll just give you a few seconds to look at these equations. And yeah, we will then move on. Any other questions so far? I'll just leave this on the screen for a bit. Okay, last slide with a bit of math. Now we start looking at actual algorithms that do all the cool things that John showed you earlier. All right, let's move on. Okay, so what did we look at so far? The goal was to evaluate a given policy, which John mentioned as the prediction problem, or find the best policy, which is the control problem, right? And the methodology that we used was given a model of the world. Now look at these words carefully, right? Given a model of the world, iteratively improve estimates with the help of bootstrapping, right? Okay, what do these words mean again? This was what we had. Given a model of the world, that means what happens if in a certain state I take a certain action, what is the next state and reward, right? That basically encapsulates a model of the world that, oh, I can just use this model to predict what will happen when I take an action A in some state S, right? Okay. Now, yeah, the second thing was iteratively improve estimates, that you take time T and then use that to get a T plus one, right? And with the help of bootstrapping, which was basically the idea of dynamic programming, that we use the answers to subproblems to solve the main problem, right? Okay, this equation looks familiar because this was just the Bellman equation, which we have converted into an update equation, right? That instead of v pi of s and v pi of s here, s prime here, we assume that the estimates that we have are reasonably correct, and then compute what the value of the state is, right? Given the current estimate. So current estimate is v of t at time t. This is what my estimate is. I use that to compute my next estimate, which is v of t plus 1. And we keep doing this iteratively till we converge, right? Where convergence means you don't, doing this doesn't change your values anymore, right? So given a model of the world, we iteratively improve our estimates with the help of bootstrapping. Okay, so there's a question. Greedy approach is giving optimal policy because we are calculating state value from goal state to the backward direction. Yeah, that's one way to think about it. That, yeah, so eventually from the goal, so like we made this intuition earlier, right? That you have a state near the terminal state, you compute what the value of this state is, right? And now the value of this state is exact. Let's say the reward was 1. So we know exactly the value of this state. Now, if there was a state preceding this with some other reward, okay, let me just make it negative because we had positive rewards back there, then we know the exact answer to the value of, let me give numbers to this state, A, B. we know exactly the value of state A. So now we can exactly compute the value of state B, right? Without going through the entire this decision process. And so we will know that the value of this is -1 plus this guy. And so at every point, as Mahendra pointed out, we don't have to take a decision if there are multiple actions from a state. We don't have to compute the sum of rewards all the way to termination to decide an action. We can greedily look at what is going on right after this action, right? Look at the immediate reward and the value of the next state, whichever of those is, let's say okay, so maybe let's take another small example. If I tell you that the value of this state is 2, value of this state is 5, but I get a reward of 1 and a reward of -3 with this action. These are two actions. Tell me what is I don't know what happens after this. Can you tell me what is the optimal thing to do in state 1, right? Based on just this knowledge. Any guesses? What is my expected reward if I take the first action? I'll get 1. And my guess for the sum of rewards from this state on is 2. So my guess for what I get with this action is 3. And my guess for what I get with this action is -3 plus 5, which is 2. So greedily, I will decide that the thing to try is action 1. And in the limit of doing this particular update many times, the greedy approach will produce the optimal solution, as I pointed out in the chat, that once we have these estimates that converge to the correct values, the greedy solution is the optimal solution, because we have exactly calculated the sum of rewards from every state all the way till termination. And then we have stored them in the intermediate nodes. And then we are just using those exact computations to decide what to do now, right? So this is what reinforcement learning is giving you, that actions can have long-term consequences, like the chess example that we had earlier, right? That maybe the action that I take now results in the death of my queen, but eventually the checkmate happens 20 moves later, right? But I don't need to see 20 moves in the future if I've already computed and backed up all those values, right? That I can just look at what is the immediate rewards that I get and bootstrap all the values of the next state. And that is all the information I need to make a decision. I do not need to look 20 steps down. I just need to look 1 step ahead. What is the reward that I get now and my expectation of the sum of rewards later, right? The reward that I get now and my expectation of the sum of rewards from that point on. And since those values will have converged to the right place, this will be the optimal decision I make. Okay, so right. So we talked about, now we'll switch gears a little bit. We talked about using this model of the world to compute iteratively compute our estimates, right? So we had this quantity, probability of next states and rewards, given the current state and the action that you took. But imagine, right? Do you do you have such an oracle in real life? Do you know that for every action that you take, how the world will look after you take that action? No, right? Like, we hope we had such a oracle to tell the future, but we don't, right? Unfortunately. So what do we do in that case? We, we interact with the world. So we don't know what's going to happen. We try it, we see what happens, and then maybe we think that if a certain similar things happen in the future, it will also have a similar consequence, right? So we can use that information to build a model in our head, right? So, for example, if in that bicycle example, that if you realize that if you are going towards a wall and you pedal more, you didn't know initially what was going to happen. You bang against the wall, you fall down, you realize, okay, if I pedal ahead when there's a wall coming in, I will hit the wall, right? So you can make a guess that next time you're close to a wall, if you pedal again, you will hit the wall again, right? And so you can sort of build a model of the world in your head like that. Um, so we can use such experience to improve our estimates, right? And because we only act with the world like one action at a time, we have to iteratively improve our estimates. So we had some guess that we want to move towards. How do we iteratively do that? How do we improve estimates from an incoming stream of data that we see? Yeah, so to answer this question in terms of reinforcement learning, let's take a step back and try to do something simpler, right? That if you have a stream of rewards, state, initial action, reward, next state, so on and so forth. So some ST, AT, RT plus one, ST plus one. You want to know what to do with this. So let's take a step back and see how do we do this in general, right? Not in context of reinforcement learning. Okay, so let's assume we had to compute the average of a stream of samples, right? So let's say we had a bunch of samples like this, x1, x2, x3, xn, xn plus 1. And I ask you, can you tell me what the average is at every point of time, right? So let's say, so far you have seen n examples. What is the average? You will tell me, oh, well, the average is, let's denote it by x bar and this subscript n that we have seen n samples so far. You'll say, okay, I can just sum up I equal to 1 to n xi divided by n, right? This is the average of the samples that I've seen so far. Now, if I ask you, okay, now you see xn plus 1, what is the average so far, right? You could tell me, well, that's simple. I can just do the same thing, right? I equal to 1. Now I'll sum to n plus 1 xi divided by n plus 1, right? Now, note that we had already summed n quantities, right? And we had this expression. Did we have to do all of this all over again? Can we do something clever? Yes, we can, right? So let me write this expression again out clear. Now, this numerator I've broken into two parts, a sum and the n plus 1th term, right? This is the average of n plus 1 quantities. Now, I open this expression and then I multiply and divide by n, right? I can do that. That's just 1. So we get n upon n plus 1, 1 by n. This is the first term and this is the second term. Okay, so far so good. Okay, so this expression is exactly this, right? The average of the n quantities. So I can write that there, can replace it, and I just write the second term as is. Okay, now I can do some more algebraic manipulation. N upon n plus 1 is same as 1 minus 1 upon n plus 1 times new quantity, right? Term including this new quantity. And okay, I will open this expression again. You get x bar n plus, I will take 1 upon n plus 1 common, xn plus 1 minus xn. Okay. That leaves us with xn plus 1 is the old estimate of the average plus I am writing this constant as an alpha times the new sample that you just saw, xn plus 1 minus the old estimate, right? So with this expression, if I just use this expression, we don't have to compute the whole sum of n plus 1 terms all over again, right? And so this is cool, right? Because this problem would have gotten harder and harder as n became large, right? So let's say n was a million. At every point of time, you would have to sum a million quantities and then divide by some, again, a large number, right? And then as n goes to the scale of billion, you have to store a billion numbers, a billion xi's, and then you have to take their average at every point of time, right? But instead of doing all that, if we just use this expression, xn plus 1, like your new estimate of the average, is the old estimate plus a constant times the new sample that you saw minus the old estimate. We did not need to store any of the n numbers here. We just store what our estimate of its average was. These are these two terms. We have this new quantity that we just observed. And then that gives us the new estimate, right? So that's a nice and powerful thing. Let me just write that out again. So in English, this would be new estimate, old estimate, plus we call this a step size times new target minus the old estimate, right? And this expression might seem familiar to you from maybe some stochastic gradient descent that you might have been learning in earlier in this week or other machine learning courses. But this is something that we will be using a lot in not just reinforcement learning, but RL but in machine learning in general, right? Okay, so in dynamic programming, we had this way of improving our estimates by using a model of the world. Then we said, okay, what if we don't have the model of the world? We can now use this idea and iteratively improve our estimates given new data that we see, right? And so that would look like this. New estimate is old estimate plus step size times new target, which is the reward and next state that you saw, the value of that state, right? You know how to compute that, minus the old estimate. So we are following this exact rule of updating our estimates iteratively and incrementally when we see new data. So remember, what was you saw some state S, you took action A, you would see a reward, and then you would see a next state. Then you would take another action, see the next reward, next state, next action, so on and so forth. So let's say at time step T, this is the state that I see. I take some action, I see some reward, I see some next state, and that is all the information that I need to compute a new estimate of the value of that state, right? That's it. We did not need a model of the world. We can do this iteratively as we see more data And so as incrementally we see more and more data, we can just keep updating our estimates till we converge, like in how we converged for dynamic programming. Okay, so that is cool. We now know two ways of evaluating a given policy, right? That we take actions according to some policy pi when we are in some state S, and we keep using that information to improve our estimates till we have converged to these the state values or the value function for that particular policy. Okay, so that is what we call temporal difference learning, right? And so in algorithmic form, it would look like this. So let me walk you through, the algorithm step by step. Okay, so we call this tabular TD learning to estimate V of pi. That is what we are doing so far. Input is the target policy pi that we are trying to evaluate. The parameter for this algorithm is a step size alpha that we discussed. So initialize the values to any arbitrary quantity. Could be all zero, right? Or could be -1s or whatever you wish. Then you'll see initial state S, and at every time step, we'll take an action according to pi. So what is the action that the policy pi takes in state S, that is A? We take that action in the world and we'll observe the reward and next state, right? And with that, we will improve our estimate of state S using the update rule that we just discussed, right? And we update the state we were in, and then this loop goes on, right? For every time step till convergence, and then we return the value V. Okay, so what is temporal difference learning? So this is temporal difference. So what is temporal? Temporal means time. Difference. So this is S prime minus S. This is something that happened at the next time step. This was what happened at the previous time step, and we are using the difference of what happened on those times to improve our estimate of a given state, right? And so that is the idea of temporal difference learning. And this is the essential pillar of reinforcement learning, if I can say that so far, like when you were doing something like supervised learning, right? If you were doing some sort of prediction or classification, you would know what your target is, right? You would know this is the ground truth, and you would improve your estimates towards that ground truth. Here, you have an estimate, and this is your target, right? Remember, this was old estimate is old estimate plus alpha times target minus old estimate. This target also involves a guess. This is also an estimate, right? So we are learning a guess from a guess. And that is what temporal difference learning is about, right? This is what separates it from the traditional supervised learning paradigm. Yep, an essential pillar of our. Yep. Okay, so far, we looked at how to estimate the value of a policy pi, right? And as we discussed earlier, right in the beginning, this is a sub goal, right? What we want to do actually is to improve our policy pi till we get to the point of an optimal policy pi star, right? And so remember that diagram we had, pi, V pi, improve the policy, evaluate the policy, all the way till pi star. Run out of space. Okay, so we now know how to do each of these steps, but we also need to know how to get from here to here, right? Okay, so before we do that, there's a question. Do we initialize all states with some random value for each state and update the state value function? Or is there a way to initialize value for each state? So that's a good question. Here, I said you can arbitrarily initialize the values for all states. So one way I could do is, this is a table, right? For every state, okay, let's call it a vector. So this is the v vector. For every state, I have some value. I could initialize all of them to zeros. I could initialize all of them to ones, minus ones, 2, minus 3, minus 100, anything, right? It would only affect how quickly we learn what is the vpi for that particular policy. Let's say the true value function vpi was 1, minus 1, 2, 3, right? And we initialized everything to 0. So as you can see, they don't really have to move too far, right? Like the estimates don't have to move too far. But had I initialized things to minus 100, plus 100, minus 10,000, and so on, these values would have to move very far to reach these true values, right? And so the initialization would affect how quickly we learn the true value function, but we would still learn it eventually in the limit of infinite data, right? And some initializations might be better than others, but that's about it. Obviously, things we can get into the subtleties of this in some of the later lectures. Okay, in TD, are we learning the policy function too, or using the greedy policy? Yeah, okay, good question. Like I said, so far, we have only been estimating V of pi. We are just doing this part. We haven't yet seen how to improve a policy, and that is what we are going to do right now. So from the prediction problem, we are now moving to the control problem, where we not only evaluate how a policy is, but we also learn how to improve the policy, right? Okay, so before we do that, John told you about this dilemma between exploration and exploitation, right? So, for example, if you are to pick some players for a cricket team, right? You could pick the players that have already performed well. So you can just exploit the information that you know, all of their scores, all of their history so far. Or you could try and do some exploration in the sense of, oh, there is these new and upcoming players. We can test how they perform by maybe trying them out on the team, right? So you always have this dilemma that, do I keep going with the existing set of choices that I've made, or do I try a new choice that I don't really have a lot of information about, right? And of course, you won't get any information till you play those players, right? And so, like, it's a chicken and egg sort of problem. So yeah, so how do we approach this, right? So a simple heuristic could be that with a small probability, we pick a random action, right? That, okay, so let's say we know reasonably well what are the good things to do, but still with, let's say, 10% probability, I'll try something completely random, right? And that doesn't seem like a bad way to do things, right? So, like, maybe I'm used to a lifestyle, let's say here, where I go to the university, go to the department, I go to the gym, I'll play some games, I will read some books. But maybe those are my hobbies. But maybe once in a while, if I might try something completely new, like dancing, right? Like I don't know the D of dancing. But I could try it sometime, and maybe that is a very fun experience that I haven't I have been missing out all my life. And if I try doing that, that will just open up something new and amazing that I have not known before, right? Or maybe it turns out I was right all the time. Dancing is not for me. But I'll only find that out if I try it, right? And so maybe this is a good policy sort of to have in life too, that not just get comfortable with the things that we are already know and are deeply familiar with, but sometimes randomly try something instantaneously, right? Okay, so all of it, these intuitions, let's try to think of this in context of some problems, right? So, okay, so let's say we have this maze in which we start from some starting state S and need to go to some goal state. These white things denote walls. Now, let's say this is the path that the agent has found so far, right? And every time I initialize the agent here, it quickly goes through this path, right? Now, imagine this was like a 2D thing, right? At every point, I have 4 possible actions: up, down, left, or right. Now, the agent has learned a policy that in this state, the best thing to do is to take the up action, right? And so on and so forth. It has learned, again, in this state, go take the up action, in this state, take down action, in this state, take the right action. But if we sort of follow this heuristic, that every once in a while we try something random, right? So let's say the agent is here. Instead of going up, it tries going back. It goes here and then comes back here and it realizes, okay, it took me more time to get to the goal because I did this exploration here, right? So maybe this was not a very good exploration move. But what if here, instead of trying the usual policy of going down, it tried an exploratory action of going here, right? And then let's say it reaches this point. Now it obviously knows what to do. It will keep doing that, reaches the goal and thinks, when I followed this new path, because of this new exploratory action, I reached the goal much quicker, right? So maybe that is the right thing to do. I should update my policy so as to do this. And this is a shorter path. I don't have to take this longer route anymore, right? And so here exploration led to a better policy, right? But as you also saw, this is not always the case. I might already know what the right thing to do is, and then I might do something suboptimal. It will take me more time, do something suboptimal, bang into a wall. All of these are taking more time, but sometimes I'll discover some new things which might be better in the longer run, right? So, okay, so that's to concretely say what this thing is. With probability epsilon, we can pick an action randomly. And with probability 1 minus epsilon, we pick the greedy action, right? The greedy action was to keep doing what you're doing, which at every point of time tells you what the best thing to do is. So the greedy action till this point was to go down, right? But with probability epsilon, which is a small number, let's say 0.1, right? So with probability 0.1, I can take any of these 4 directions. Sometimes at some point, I might end up taking this and discover something new, right? And so this is called epsilon greedy action selection. That we are almost doing everything in a greedy fashion, but epsilon amount of times I do something randomly, right? So this is called epsilon greedy. And this is a mechanism of exploration we can use while guaranteeing some sort of exploitation as well, right? So the greedy part ensures exploitation of the knowledge that we already know. The epsilon part ensures some exploration, right? Like maybe 10% of the times or 5% of the times, whatever this epsilon is. Okay, so now we are ready to see our first control algorithm, which is SARSA. Again, let's walk through this algorithm. SARSA to estimate Q, which is Q of pi star. Okay, remember Q was our action value function, pi star was the optimal policy. So we are approximating the optimal action value function. Parameter is just the step size. Initialize again for all states arbitrarily to 0, -1s, -100s, whatever. Observe initial state S. For every time step, we pick an action according to the policy derived from Q, right? So this could be an epsilon greedy policy with epsilon, let's say 0.1. We take that action, we observe the next state and reward. Now we also select the next action, again, based on the same epsilon greedy policy, right? So the same policy that we used here, we'll use here too. And then we make this update, again, in that same fashion. Old estimate is old estimate plus step size, new target, reward plus action value of next state and action pair minus old estimate, right? And then keep doing this till convergence. And okay, so this works. This will let you converge to the value of the optimal policy. Why is this called SARSA? That is because you have state, action, reward, next state, next action. These 5 quantities are required to compute this update, right? And so that's why this is called SARSA. This is also known as a non-policy algorithm. We'll see just in a moment what that means. Okay, moving on to Q-learning, which is, I guess, something that you must all have heard by this point from all these big successes of, DQ and Atari. All of these things have started from a version of this algorithm, which is the Q-learning algorithm, right? Okay, so what is this? How is this different? Everything is the same as SARSA so far, except the next state, you pick an action according to the greedy policy and greedy policy alone. This can be an epsilon greedy policy, but the action for the next state is always the greedy policy, right? That gives you this update again. But I want you to take another closer look at what this is, right? If I'm taking the action according to the greedy policy in state S prime, do you remember from the equations that we learned earlier, that Bellman equation, Bellman optimality equation, how did things change? Right, so this Q of S prime, A prime here, can I replace it by this thing, max of A, QS prime A? Is that exactly what the greedy policy would give you? Yes. And so you can, line number 6 and 7 are equivalent to this expression that we have written in white. And that is the Q-learning update. And that will, if you recall, look similar to the Bellman optimality equation that we had derived for state values, for action values, Q of SA, right? It had this expression at the end. And so Q-learning is just, we had dynamic programming, we got to TD learning. So the dynamic programming equation for like the Bellman optimality equation, the TD version of that is basically Q-learn. Right? Okay, the details are not very important, but for now, and so we can just move on. And okay, so this is the off policy algorithm. What does this mean? There was one policy with which we picked the first action, but the second policy was different, right? It was always the greedy policy. It was not an exploratory policy like this one. So this is off, like it's not exactly, okay. So the previously in SARSA, we did both of those things according to the same policy, right? So everything was on policy, but there's something off here, and that is the off policy, right? Okay, so minor this thing, you'll get to use and learn more about these algorithms in the lab part that you'll do later today. Okay. Okay, so we are coming towards the end. So let's start wrapping up that. Okay, so we are planning, how do we plan using a model of the world, right? So we studied one way to use a model with dynamic programming, right? This was the update equation that we had. This is how we use the model. Then we can also use a model of the world as a substitute for real world experience, right? Okay, so what does that mean? You saw a diagram like this in John's lecture. There's an agent. It sees an observation from the world, takes an action, sees the next observation, and so on and so forth. This is the real world. What if I tell you that we can replace the real world by a simulation of the real world, which we call the model, right? Matrix, we're living in a matrix. Anyway, so this is, we can use the model of the world just as a substitute for real world experience and then make the usual TD-like updates. Okay. To make this update, the update doesn't know where these rewards and next states are coming from, right? It could have come from the real world, or it could have come from the model of the world. And so the update doesn't know that. And the update, you can make the update from data that comes either from the real world or this model of the world that you have. And this intuition is, we can sort of, okay, why we even moved to TD in the first place was because we said that, okay, where do models come from, right? Where is this oracle of the world that we don't have access to? And then I give you some example that banging into a wall will teach you that next time you're bicycling close to a wall, if you bicycle forward, you will bang into it, right? So you can learn a model of the world from experience. And we can, how do we do this? Okay, so here I'm giving you some data, right? And I tell you that capital letters denote states, small letters denote actions, numbers denote rewards. So capital A, capital B are states, T is a terminal state, small a, small b are actions, and these numbers are rewards. So can we try to think about what sort of world would lead to such an experience of data, right? So let's say this is state A. I take action A, receive reward 1. So we are looking at the first trajectory, right? Action A, reward 1. I end up in state B, right? So far we've looked at A1, B. Now in B, if I take B, I get reward of 1 and then I terminate. B, reward of 1, then I terminate. Okay. This is the first trajectory. Second trajectory data tells us in state A, if I take action B, I get a reward of 0 and in C. Take B, reward of 0, end up in C. If I take action A in state C, I get a reward of 3 and I end up in T, terminal state. Okay, that is the second trajectory. The third trajectory tells us in capital A, you take A, you get 1. Okay, we already knew that, end up in B. Then it says, if you take action A in B, you get a reward of 0 and end up in the terminal state. Take action A, reward of 0, end up in T. Finally, the last trajectory tells us in capital A, you take action B, reward is 0, end up in C. Okay, we already knew that. In C, if you take action B, you get a reward of 0, end up in the terminal state. Okay, so now this world that we have built exactly generates all of this data that we have seen so far, right? And so we have built up a model of the world from some real experience. And then we can just store this information in terms of any data structure, right? So for example, I'll just have a table which tells me in state A, what happens if I take action A? I get a reward of 1, end up in state B. If I take action B, I'll get a reward of 0, end up in state C, right? And so I can do this for states B and C. And that's how I can build a model of world from experience, right? And so we can put all of this together in this algorithm called DYNA, right? This is also a central algorithm in reinforcement learning, which integrates this idea of learning and planning, right? Where planning means learning from a model. So as usual, we want to estimate what the value of the optimal policy is. We take a step size, initialize the action value estimates and the model for all state and action pairs. See state S, take an action, which could be an epsilon greedy action, observe reward R and S prime. The next thing we'll do, we will update our model. We'll say, okay, usually in state S, when I take action A, I see R and S prime. Okay, so I'll just note that down in my model. And then using all this information, I can have a loop which picks a randomly a previously observed state, a previously picked state in this action in this particular state. There should be a subscript P there. And then I'll consult my model and say, okay, what happens when in state SP when I take action AP? The model tells me, oh, from our experience, it usually ends up with reward RP and SP prime, right? And then we can just do the usual Q learning sort of update on this experience that came from a model, right? So this is imagined experience that we learned from real world data. And then we just doing this till convergence, right? So this was an algorithm that let us learn a model as well as plan with it as if we had real world experience, right? Okay. So now you know a lot of reinforcement learning. Let me just leave you with this final topic, which is policy optimization, right? So far, we've used value estimates to improve a policy, right? We went through this process. We learned how to evaluate a policy. We learned how to improve it greedily all the way to get to pi star. What if we could directly improve the policy, right? Directly go from pi 0 to pi star. So yes, there is a way to do that. And we'll do it by the means of policy parameterization, right? So in all of these value-based methods that we saw so far, we picked actions based on a learned value function, right? That you would take the action in a state would be the action that maximizes our action value function, right? So if you had a state and you had many possible actions, you would look at what Q is QS A1 greater than or equal to Q of S of A2. If this quantity is better, you pick this action A1. That is what the argmax would give you, else you pick A2. Now, in policy-based methods, we do not need to consult a value function to select actions. So here we are consulting a value function to select action, right? In policy-based methods, we don't do that. Instead, we use action preferences that we can learn, right? So let's denote a preference for a particular action in a state by h of SA. How do we, our policy needs to be a probability distribution, right? That it should sum up to 1 for all states. So this is one way to convert our preferences into a policy distribution, right? And do you see any problems with this? Well, the most obvious one is, what if this denominator is 0? When can the denominator be 0? When these preferences are like, some are positive, some are negative, or maybe all of them are 0, or things like that, right? Well, to avoid that, we can take this exponential function on both sides, numerator and denominator. This ensures that both these quantities are always positive, right? Irrespective of the sign of your preferences. And this thing is called a soft max, right? So here you had a hard max, and that, but now you have something called the soft max. Okay, that's where the name comes from. And so how do you learn these action preferences? Let's just consider the very simple case, right? There is just one state. So, and your objective is to maximize the amount of reward that is obtained, right? That is the goal of RL. And we'll do something like stochastic gradient descent. So recall that under the softmax policy parameterization, the probability of taking action A is given by this softmax, right? E to the preference for that actions and sum of all the exponents of all the other of all actions, right? And for all of these actions, this will sum up to 1. I'll tell you that the update rule ends up like this, that for the action that you took at time step t, here's how you'll update its preference. If the reward that you saw, compare it with the average reward that you've seen so far, right? Look at this quantity, 1 minus probability of picking that action. So this is always non-negative, right? Greater than equal to 0. So what will determine whether this thing is greater than the old estimate is whether this thing is positive or not, right? So let's say that the reward you saw is better than the average reward you've seen so far. That means we want to, that seems like a good action, right? That you want to increase the probability of taking a good action. And this rule would do exactly that. This quantity would be positive. This is always non-negative. So this is a positive quantity. You will add it to this. You will increase the preference for this action. For all other actions, so A not equal to AT, if this thing was positive, if your action resulted in a reward greater than the average reward, positive, 0 minus pi A. So this is always non-positive, right? Because pi A lies between 0 and 1. So for all actions that was not this action, this will be a negative quantity, which means you are reducing the preference for all other actions. And this makes all intuitive sense, right? You took action 80, it resulted in a reward better than the average reward. So you increased the preference for that action. You decrease the preference for all other actions, and resulting this increase and decrease of preferences change your policy, right? You increase the probability of taking this action. And the opposite thing would happen if this reward was less than the average reward, right? You took a bad action, it resulted in a small reward worse than your average. This quantity is negative. This is always non-negative. So you will end up decreasing this quantity and increasing the preference for all other actions. Negative, negative, positive. So this rule makes a lot of intuitive sense, right? And this is called the gradient bandit algorithm. So note that there are two things that are happening here, right? I have a policy, and I have what we call a baseline that we are comparing things against, right? So you can think of this as an actor, that an actor is picking actions, and then there is a critic which is critiquing the actor's actions, right? That if the action was good, it will tell it to improve the preference. If it was a bad action, it will say, oh, decrease the value of this thing, right? So this is an actor, this is a critic, and this is the basis of a famous family of algorithms in RL called the actor-critic algorithms, right? And you'll learn some details of this in lecture 3. And yeah, that is about it. This was a whirlwind tour of what the nuts and bolts of reinforcement learning are, with starting with dynamic programming, temporal difference learning, model-based RL, which was the DYNA algorithm that we talked about, and then policy optimization in terms of gradient bandit and these actor-critic algorithms, right? And yeah, let me just get back to the questions after this. So all of this was very quick, but hope this gives you a flavor of what these algorithms look like. And if you want to know more, this is the best source for this, which is the RL textbook by Sutton and Barto. This is available freely online at this link that is at the bottom of the slide. You can download the PDF, and all of the material that you've seen in the slides today and in the previous lecture are in some form from this book, right? And this is like basically the book to get started with RL. And I would highly recommend looking into this free textbook online if you're interested in what we talked about so far. And yeah, thank you so much for your attention and time. If you have any questions, go ahead. And this is just some quick contact information.
Hello, Abhishek.
Yep.
Yeah, I'm Rosik. Actually, we are hearing you from the hall. Perhaps you can see us in the camera.
I do. Yep.
Yeah, we might have some questions from the hall too. So
yeah, sounds good. I'll be happy to take them. Maybe quickly I can take the chat question first, because I guess that came before.
Yeah.
In the gradient bandit algorithm, we are selecting action by sampling from the distribution given by the softmax function. Exactly. So the softmax function tells us that the probability of picking different action, let's say we had 4 actions and the probabilities were 0.8, 0.05, 0.05, 0.1, right? And so then you would, this is a distribution over actions, you would sample a random number between 0 and 1, pick one of those actions, right? And yes, so the answer to your question is yes. Any other questions in the chat or, yeah, right, just here. Yeah, there's also a Discord for this particular school, so you can ask, you can post any questions there later too, and I'll try to get back to them as soon as possible. We have a big time zone difference, so it might be a few hours before I can answer those questions, but yeah, I will definitely get to them soon. So yeah, feel free to post questions there, and if you need to ask me something in particular, my contact information is up there on the slides. And yeah, if there are no more questions right now, I would like to thank the organizers again for giving me this opportunity to come and introduce some basics, essentials of RL to all of you folks. And I hope you found something interesting that you can sink your teeth into. And over the rest of the day, you will hear a lot more interesting details and applications of what you can do with RL, and then actually get to try some of them out in some of these cool lab sessions that the rest of the organizers have designed for you. So I'm excited for you, and I hope you have a good time for the rest of the day.